Hello everyone, welcome to this webinar. The subject today is accelerating deep learning for vision using Caffe. I am Yassin Hariri, Senior Engineer at CMC Microsystems, and my full focus at CMC is around heterogeneous computing and accelerating machine learning frameworks. So the agenda for our presentation today is as follows. After a quick introduction of CMC Microsystems, we're going to have a high-level overview and quick recap of AI applications and deep learning. Then we're going to highlight some of the main features of Caffe framework as a machine learning framework. After that, we're going to have a step-by-step guide in order to train a model. So this includes data preparation, CNN model definition, solver definition, and model training. After that, we're going to have a presentation of a technique called transfer learning, which is used to fine-tune our trained model, and a live demo and instruction on obtaining this flow and reference design, also access to the heterogeneous processing platform, the platform we are using in this project. Finally, we're going to have a quick introduction of the upcoming CMC Cloud infrastructure, and we're going to conclude this webinar with a Q&A session. So, CMC Microsystems is a not-for-profit corporation, federally incorporated since 1984. The main goal is to manage the Canadian National Design Network, and the objective is to deliver micro-nano innovation capabilities across Canada. The National Design Network is a collaborative project between 66 universities and colleges to connect 10,000 academic participants with over 950 companies, and the main goal of this collaboration is to design, make, and test micro-nano system prototypes. Here are some statistics about our community. So annually, CMC connect to 1,200 connected professors, 4,200 researchers, 5,700 users of CAD tools, 300 physical prototypes, and 80 test equipment loans. We measure the outcome by the number of publications and patents awarded and applied, industrial projects, as well as new startups and high qualified personnel that move to industry. Basically, CMC deliver key services to increase researchers and companies' innovation, and these are the main elements: design tools, including software, fabrication services to create working prototype, equipment and services for prototyping and testing, platform technologies, training, and technology plan and roadmap. The global sources of essential microsystem technology to support researchers. So these are the strategic engagement and global partners in North America, Asia, and Europe. And here are some statistics about these global partners. We're going to have a quick recap of AI applications and deep learning just to give some context of this webinar. So this link to a project that CMC has been awarded from the National Defense. It's a project IDES, Innovation for Defense Excellence and Security, which consists of developing a novel platform for AI-based object detection, classification, and tracking using heterogeneous computing architecture. And this diagram shows a high-level overview about this project. So basically, it's divided to two main sub-projects. The first one is develop a training demonstration of a CNN network and mapping it to a heterogeneous computing platforms that combine FPGA with GPU and other accelerators. And once we develop this training architecture, we are planning to deploy it for inference to an embedded device. And we selected Xilinx ZCU102 development board to do that. So basically, there are 5 steps in this project. The first one is the data curation, which consists of selecting a database for the training. And the second step is network design. So in this step, we plan to evaluate different CNN architecture for training and get the best results. And the trained model will be optimized and deployed for inference. And the inference consists of building an application that uses the training CNN, and we do fine-tuning for this, and we deploy for in the field. So basically, the webinar today cover the training for these projects, And the whole platform will be available to the National Design Network, to the professors and researchers, and also to companies to experiment and demonstrate this platform with your own data. So this is the context of this project, and we're gonna talk a little bit about the basic steps to do training using Caffe framework. Before that, a high-level introduction to AI. This is widely accepted definition. So broadly speaking, the objective is to mimic the human brain. So an AI system is a system that has sensors that can reason and act and adapt. It uses basically machine learning algorithm that improves as they are exposed to data over time. And deep learning is a subset of machine learning, which consists of using deep neural network that learn from vast amounts of data. Convolutional neural network, as we're going to present today, are the main neural network that are used in deep learning, and they have a very good result for computer vision. AI is, this slide summarizes the area of specialization. It is used almost everywhere: gaming, natural languages, robotic, computer vision, autonomous car. But something we notice is that there is explosion of ecosystems and tools which make it more accessible to even non-experts. So as we're going to see today, using Caffe, you can train any model that is available on any data set. So we are going to provide all the steps required to do that. So, as you know, machine learning is not something new. The first CNN model was designed in the late 80s. It's called LeNet. But starting by 2012, there was an increasing interest in machine learning. And it's good to summarize what are the key enablers for this innovation around machine learning. First of all is the greater availability of large data sets containing more training examples. Today you can access a lot of databases on internet and use them for training your model, fine-tuning for a particular task. As an example, ImageNet contains thousands of classes, and each class has thousands of images easily accessible, and you can use them to train your network. The second thing, since CNN are compute intensive, so the availability of very high performance accelerators such as GPUs, mainly for training, and FPGA, mainly for inference, and other custom hardware such as TensorFlow, is a very good enabler. Today you can train a network extremely fast and deploy it for inference. Not forgetting something also very important is innovation around the algorithm, open source for machine learning flow, as well as libraries, which make it easy to design for this application. As an example, there are many CNN models available, as we're gonna see in one of the slides, that are different variants of CNN, including CNN, GoogleNet, AlexNet, and other. So we're going to compare this, and we're going to use one of these CNN models for this demonstration. This slide summarizes the deep learning framework available today. There's TensorFlow, Caffe, Torch, Diano. We already presented the flow using TensorFlow on the HPP, and today is Caffe. And just to have a brief introduction to Caffe for people that are not familiar with this flow. So it is an open source. It means you can access it, you can access the source code. It's an open source for deep learning framework developed by Berkeley AI Research. It is developed using pure C++ CUDA architecture, which makes it a well-tested code with seamless GPU acceleration. Basically, GPU acceleration use a vendor-specific libraries called CUDA neural network to accelerate a lot of tasks on the GPU. It supports for command line, so during the demo, we're going to see how to use Caffe on command line to do training and deployment. And it has also Python and MATLAB interfaces. It has a very rich ecosystem of tools to do pre-processing of data before training. It has also a lot of reference models and examples that you can use to start using Caffe. Image data management is another feature. So since we deal with a lot of training algorithms, accessing data in a very efficient way is very important. And a large community of contributors to the open source. So there's over 150 contributors. It is available on GitHub, and here are some statistics, over 600 plus citation, 150 plus contributions. The bottom line is that this framework is improving every month. You will see something new, some good contribution from the community, and it's easily accessed. What is Caffe? Caffe is an end-to-end deep learning framework, and here are the main steps. These are basic steps. In the beginning, you don't need a high performance computing cluster or node to do that. So just your laptop to do prototyping, to make sure it compiles, your model compiles, and once you are comfortable with your model and with your framework, you can deploy for training using GPUs. NVIDIA GPUs are all supported by Caffe, most of them. And then you can deploy for inference either on a high performance computing center or on an embedded device. Of course, the requirement for deployments on each space is very different. For example, for the embedded space, you need to do a lot of optimization. You need to change the resolution of your weight, and you do a lot of optimization of your network to fit within the model and to consume less power. This slide summarizes just the steps to install Caffe. We will make available with this webinar a guide to install it, but just to highlight some of the main feature, the main prerequisites, they are available in the makefile. So in our case, in the demonstration today, we compiled Caffe with CUDA Toolkit 10.0 with NVIDIA CUDA. These are the latest one. The OpenCV 3.0. BLAS is the basic linear algebra, which is used basically to do matrix multiplication, addition, and all the basic linear algebra operation. Boost, a C++ library, which offer math function and shared pointers. Glock and GFlag is providing for logging and information command line utilities, which are essential for debugging. LevelDB and LMDB, these are very important features because they are used to deal with databases during the training. So we are going to format our images using these formats. And protobuf, which is an efficient and flexible way to define data structure. So once we have all these prerequisites, we can just issue a command using make, and we compiled this Caffe framework from source on a workstation that has Ubuntu 18.04. I didn't mention it in the slide, but this is the actual version. So some of the main features of Caffe, the first one I would like to highlight is the data pre-processing and management. When you compile Caffe from source, you have access to a lot of tools that are in binary format, so you can just execute them from build tools. And the first feature is the type of data that Caffe can ingest. So there is a lot of different formats that you can use. The first one is LevelDB, LMDB databases, which are an efficient way to access data during training. And the second one is more simple to read, which is HDF5, which deal with a huge amount of data. Or you can process image by image, which is not very efficient. So in our case, in the demonstration, we use the LMDB, and we are going to show how to prepare data for this database. The pre-processing tools, as I said, these are scripts that are already compiled from source and available to use. They allow to create the LMDB database from raw images. The generation of the mean image, which is used in the pre-processing before the training, and training validation sets creation with shuffling. So we need to shuffle the data before creating the LMDBs. There is also some tools for data transformation, such as image cropping, resizing, scaling, and mirroring, and mean subtractions. And these tools are used, for example, resizing is used to change the resolution of the input images to fit with the selected network. We are going to have a good example for that. The second feature I would like to highlight is the model format that Caffe use. It's called protobuf. It's a format developed by Google, and it's a good method of serializing structured data. As you see in the right here, the example, it's human readable, and it's used mainly to define the network architecture and the training parameters for your CNN network. So no coding is required. And you can already browse and see the available example of networks. Here, for example, we describe a convolution.
Sorry for sending the last email.
Other blocks, some parameters for the training, and some parameters for the size of the convolution, the number of output, the padding, kernel size.
Mistaken.
So for someone that starts using Caffe, I don't worry about understanding all these parameters because we are going to use some predefined models. But for advanced users, of course, there will be a lot of things to learn in order to create models. The functions that are used in the proto.txt in this model file. So we need to know which functions that are available. These are building blocks for convolutional neural network, including the basic blocks for data processing, including convolution, polling, normalization, and how to process the data. There's loss functions here for the stochastic gradient descent in order to do the optimization of the weights, and of course the activation function. And here at the bottom of the slide, just one simple example of a CNN network. So it's a deep neural network. It takes an image as an input, and you have two main blocks. The first one is feature extraction, followed by classification. And as you see here, the feature extraction use a series of layers to process the images in 2D dimension. And basically, most network, AlexNet, GoogleNet, and VGG, this network use a series of convolution and pooling and activation layers. As for the classification layer, it uses a fully connected network and matrix multiply. And the main objective of this network, for example, is to provide for each class ID a probability that the class is the image. For example, here we have 0.9 is the highest probability, and it's about. So this is the main objective of CNN, is to provide a list of 5 top or 10 top probabilities, highest probabilities for classification of an input image. This is for inference. As for training, we are going to look at some examples to highlight the feed word, the loss function, and how it updates the weights of the network. It's another architecture. So, because we use CNN, we just want to highlight some of the history. Began with AlexNet in 2012, and this at my left is it shows the increase in terms of accuracy of the available network. These are networks developed by companies and community, and the accuracy is increasing. There's a lot of and all these most of these networks are available to train with your own data. As for the right side, we have the entire operation.
Not quite sure if I'm going to attend each network. Once I decided.
So for deep neural nets, so no coding is required. The first thing we would like to highlight here is that you can train your network using one command, Caffe train, and all what you need to provide is the name of your proto.txt. This is the solver that you are using to train your network. So the solver provide information that link to which model we are training. In this case is googlenets.proto.txt, and with some parameters for the training. In this case, the solver computes the accuracy of this model using a validation set every 10,000 iteration, and it takes a snapshot of the training results each 5,000 iteration, and it saves it on GoogleNet snapshots. So, and here we use the GPU for acceleration. So this is mainly the how you launch a training. You need a solver, and you need to provide the name of your proto.txt. The result is an output to std out, Of course, these results offer a good idea about how the training evolved, but it can be used to extract very important information on the curves, the learning curves of your training, and we are going to see an example of that. Before we dive into the step-by-step procedure on how to train a network, here we would like to highlight one of the main important feature is that Caffe models for different tasks with all kinds of architecture and data is available on something called Model Zoo, Caffe Model Zoo. And it's a standard format for packaging Caffe, so you can either download one Caffe model and use it with your application, or you can contribute to the Caffe framework by uploading your own model. So basically, there are a variety of models available that we are going to see. In this case, we are using CaffeNet, which is a variant of AlexNet. Now, this part of the presentation describe really a step-by-step on how to train any model on any data set. This is really practical. So if you are interested in doing training some examples with Caffe, this is a very good starting point. The first step is data preparation. In the context of the project, we have selected a database called the RSD database, which is an extension of the UC Merced archive. It contains 2,100 images. Each image is a resolution of 256 by 256 pixels. And these are 21 class labels. So these are the different classes that we start with for this project. The first thing is to prepare this data for training. So we will deliver with this webinar some reference design and scripts on how to do that. The first step is to create a training and validation databases from this data set that can be ingested by Caffe. So we have already prepared two main scripts. The first script copy all images from all directories to one directory, and it creates two files, train.txt and val.txt. This is for training and this is for validation, required for the training validation. And the second script take the results of the first script. It resizes all the images to 227 resolution, and this is the resolution that will be accepted by the neural network CaffeNet that we will use. And it will create train LMDB as well as val LMDB, which are our databases for training and validation. There's also to highlight that we use make mean, which is available by Caffe. We didn't create this file. This is already available in the installation, which creates the mean image. So to highlight how this works, so we take we download the database, we unzip it. We have all these different categories in different directory. So the first script take all the images from all these directories and copy them in one directory and create the validation and train these two files. They are important in order to create the database. Each file, for example, the training file has all the name of the file that will be used for training, space, the class ID, and here we highlight that this is a supervised learning. So the data we will feed into the network should not only provide the image, but also the class of the image. And in this case, we created the 80% of the database is used for training, and 20% is used for validation. So once we have all this ready, we run another script which take these two inputs and generate our train LMDB and val LMDB, and these the databases that will be used by our CNN model, and basically by any CNN model. Now, once we have prepared the data, we will go to the CNN model definition. And in this case, we need to select a CNN architecture and define its parameters in a configuration file. The extension is proto.txt. And in our case, in this demo, we show how to change the CaffeNet train val, which is taken from the database of the Caffe Zoo. and do some modifications in order to adapt it to this particular problem. So in order to fit this model with our problem, we need to update the inputs for the input path for training data and validation data. And we also need to change the number of classes that will be used since the original model is trained on ImageNet, which is 1000 class. We need to change the fully connected to 21 outputs because we have 21 class in our problem. So these are the modifications. So we changed the path and the proto.txt. This is a textual file, proto.txt, which describes the network as I showed previously. And we just need to go to this file and change the path to this training and validation data sets, and changing the last fully connected to 21. So this is very minor changes to the original file. We can actually visualize the resulting network by just issuing a Python command, drawnet.py, which is available in the installation. And we provide as arguments the name of the proto.txt that we would like to see. In this case is this one. And we can generate the output file in an image format, PNG, and we can actually just open it and look at the different block of this CNN. The solver definition is the last step that we need to define. It provides the path to the model we would like to train, which I described previously. It also set which accelerator we would like to use, in this case GPU, and the directory where we would like to print or to save the status model. So for each 2000 iteration, we have a saving procedure to save the weight of the network. I won't worry about all these parameters. They are here used in order to guide the training process. So there is already documentation on the Caffe website on how to set these parameters, basically. But they are parameters for the training, to guide the training, actually. So model training, we issue a simple command, Caffe train. We specify the solver. In our case is solver_1 proto.txt. And we generate the train log, which is basically the training result. It will be saved in a file. After that, we can plot the learning curve that is obtained from this training log. In our case, this is the first result of the training on the data set we have described. We observe that we achieve an accuracy of 85%, and it stopped improving after 4,000 iterations, which is not surprising because we train a model from scratch. And as a next step, we are going to describe how we can improve this 85% using transfer learning. For the acceleration, we have a speed up factor of 11 by using GPU in combination with CPU. And these are the accelerator we are using Tesla Pascal P100 and Intel Xeon as a host processor. So it's not surprising because GPU has a lot of acceleration in this case. Now we are going to show how we improved the results for this particular case. So we use what we call what is already you might aware of, people who are in the machine learning space, transfer learning. The issue is why we obtained the very modest results because CNNs requires large data sets and a lot of time to train. And some CNNs could take up to 4 weeks. So the solution is transfer learning, which consists of, instead of training a network from scratch as we did, we use transfer learning that will train an already trained model on a different data set. So this is called fine-tuning the trained model. So I'm going to train the model on a new data set by continuing the back propagation of the last layer. And we can either, in this case, fine-tune the whole network or freeze some of its layers. In this case, we are going to find the whole network. So how we are going to do transfer learning? First of all, we need to download a pre-trained model, in this case from the BVLC reference CaffeNet as a starting point. And the model was trained on an ImageNet database, dataset. So we need to download all the weights. It's a file of 300 meg, and this is very simple how to download the file. So you just need to issue wget and provide this path. Once you execute this command, you're gonna have in your directory the weight of the pre-trained model. Now there are some modifications to the proto.txt to make it work with the transfer learning technique we are applying. The first thing, as we described it before, is just to point to the input data for training and validation, so no change here. But here you need to do two changes. The first one is to change the name of the last fully connected layer from FC8 to FC IDEA, and change the number of outputs. So basically you are telling Caffe to train for a specific problem using the weight that we just downloaded. So it's very minor changes to do this transfer learning. And then after defining the model and the solver, we can start the training. And this is different than the command we issued previously. Now we have to specify the weights that are used. And this is the weight we have downloaded from the BVLC. And we generate the results. Now, we obtained it before 85%, I think. Now, the results are very good because we used a pre-trained model as compared to training a model from scratch. And we see here we achieve an accuracy of 98%, but after 1,000 iterations. So there is a lot of learning already transferred to this new model. And it's a very good way to obtain very fast results and very good accuracy. With a live demo and instruction on obtaining access to the flow, I will switch window to the server we are using in this project. So new share. And I'm going to log to the workstation. I apologize here. I need to change the resolution of my screen. So let's try this. So I'm gonna keep this change. And now we can see a lot of information. The first thing I would like to highlight is the Caffe installation. So I'm gonna open a terminal window. And once you install Caffe, you will have a directory called Caffe. So if everything is fine, you will have this directory, and you can browse this directory to look at its content. For example, here you have some good examples that come with Caffe, including feature extraction, how to use HDF5, etc., etc. But before installing Caffe, you need to, before issuing a make, this is a very good file to look at in the beginning. It describes what components of your Caffe installation will have. For example, here you define that you are using the accelerated CUDA neural network libraries from NVIDIA. You also can provide which version of OpenCV you are using, and a lot of other parameters that you will see depending on what you are trying to achieve and what type of resources you have in your workstation. With the reference design, we are providing a README file that allow you to go step by step and replicate what we have done using the script we have provided. But for now, we are going to see some demonstrations. So I have here the the directory that contains all the images and information. So this one. So initially we have downloaded this zip file, which we unzip here. So all the images are here. And the script I have described in the beginning take all the images and put them in one directory. And these are train validation images. So all the images are here. And as you see, the train and validation text files that you can look at, they provide for each image, it's the class of the image. And they are shuffled because training, you need to shuffle all the data before start using it. So once you have that, this is the solver we are using in this particular case. So I already showed this in the presentation. And what about we see an example of how the training is done. So basically, we will just take a Caffe command. The first thing we need to do is to set up the environment. So we are using CUDA 10, and we need to provide the path to CUDA 10 and to Caffe and to Python. So we just copy these scripts here. And then we will just issue a simple command to do the training. Basically, this command. So when I hit enter, the training process starts, but I just would like to highlight what information you need to look at in the beginning. So the training starts here. First of all, it will display the solver file you are using. And it will explicitly show you the accelerator you are using in this case. So it will show you which accelerator is used for the training. In our case, it's a P100. And after that, it will compile the whole network to see if there is an error or problem. And it will proceed to the training. So in that case, you just take a coffee and come back to look at the results. But we are not going to wait for the training because it's going to take almost half hour. We are going to go back to the presentation and look at the other contents. And if you have questions, of course, you can ask them at the end. So I will go back to the presentation. This one. So I've seen a demo. This steps, and it's a very good starting point to train any model or any data sets, as long as you have the same structure of the data, and you modify the network as well as the solver to fit with your application. It's going to work. The rest of the presentation, I would like to just give a high-level overview about the upcoming CMC Cloud infrastructure to support research in Canada. And we have a slide for that. This is a unified architecture which offers a seamless transition between environments. So here we have mainly 4 components. The first one is the storage, of course, that you need to store your data. And there are 3 different clusters that will be available. The first one is a compute infrastructure. And this is mainly to accelerate CAD tools using CMC Cloud and fab services to simulate the CAD compute cluster. And the third one is lab prototype on FPGA and GPU. The demo you just saw is one of these nodes. So the framework we are making available today can run without any problem on this cluster. And you can run on one node and scale up to the other nodes. And to give more information about this cluster, so the first one is the cluster that is used for CAD tools. Here's some specification. It's very fast, and it's used to accelerate basically ANSYS, CAMSOL, Xilinx, and other tools. And the one that is more relevant for this presentation is an 8-node, and each node has a Alveo FPGA. This mainly will be used for inference. We didn't show it today, but it will be shown in the next webinar. And a GPU V100, which is a very good GPU to do training on medium to large networks. So this is going to be available fairly soon, maybe in April or early May, and we will provide access to people to use it. The way to use this is either you can use different nodes using data parallelism to train different networks, or you can split the network on different nodes, and then you can accelerate training in these two different ways. The software stack that will be available, of course, Caffe, as we present today, but there is also TensorFlow and MoxNet. It's a complete software stack. The programming models and runtime include OpenCL, Python, and C++. And of course, the middleware and libraries from vendors, including CUDA neural network and other libraries. So this is the complete software stack. So I think we presented all the content we need to present, and now with 10 minutes of time for questions, we're going to pick up some questions from the chat window. Back to you, Brent.
Yeah, there have no questions have been posted yet, but please feel free to do so.
Can we see the questions?
I guess if there's no questions, you can end it, Yassine.
Okay. So feel free to contact me if you have any questions.
Oh, wait, sorry. One question just came in about Caffe.
Yeah.
Looking for an explanation Caffe 2.
Yeah. So in this presentation, we used Caffe because it has everything we need for this project. Caffe 2 is a very good framework as well. It's a variant of Caffe that is more suitable for the embedded space. So if you really need to train a model and deploy it on an embedded device, such as ARM processor or Zinc FPGA, which has a heterogeneous processing platform, FPGA, GPUs, and tightly coupled with the host, then use Caffe 2 because it has a lot of accelerated libraries for inference.
Okay, another question related to the same code for MATLAB.
We didn't need to use MATLAB in this project, but if there is interest to that, we can look into that and make something available.
So they would just reach out to you directly?
Yeah.
Question about the preference between MATLAB or Python.
MATLAB and Python. So MATLAB, it has a lot of features, as you know. You can use MATLAB to do a lot of pre-processing of data. There's a lot of acceleration libraries as well. Python is more for someone who has expertise with Python, and you need a lot of, the learning curve is not the same. Is it possible to train CNNs with ImageNet dataset using CMC Cloud? Absolutely. It will take you 3 weeks, but it is possible.
What about the transfer?
How we can transfer dataset to the cloud? Once you have access to the cloud, you will have enough space to just issue an wget and download the dataset you need to the cloud. But for the heterogeneous cluster I talked about, there will be some use cases, and there will be already available some good data set to start with using Caffe or TensorFlow. So if we don't have any further questions, I would like to thank everybody for joining this webinar today. Please contact me if you have any any questions or feedback.